Good evening, everyone. We are students from the Department of Electronics Engineering, Vidyalankar Institute of Technology, Mumbai. Our project is titled Design and Implementation of a T-Junction Traffic Light Controller using Moore Finite State Machine in Verilog HDL. The project was carried out by Swayam Navle, Maitry Mohite, and myself, Vishwajeet Patil, under the valuable guidance of Professor Akhil Masurkar. This work focuses on building a hardware-based traffic controller system that can make urban intersections more efficient and sustainable using digital clock design and FPGA technology. With the rapid pace of urbanization and vehicle growth, cities are facing major challenges due to increasing traffic congestion, particularly at T junctions, which handle both merging and diverging traffic. To address these challenges, our project processes a finite state machine FSM-based traffic light controller implemented in Verilog HDL. Specifically, we use a Moore FSM architecture where the outputs depend only on the current state, ensuring predictable, stable, and hazard-free transitions, an important feature for safety-critical systems like traffic management. By implementing this on FPGA platform, we achieve fast, deterministic control, low resource utilization, and high scalability for smart traffic systems. Now, the literature review for this project done by us is before starting our design, we reviewed several research works to understand existing approaches and their limitations. First, Law et al. 2022 to 2021 developed a smart traffic light controller using deep learning and image processing for four-way junctions. It achieved a 94% vehicle detection rate, but was computationally heavy and unsuitable for real-time FPGA use. Second, Reddy and Somya, 2017, implemented a Verilog-based FSM traffic controller on FPGA, adding emergency detections and camera integration. However, it was designed for four-way junctions and did not optimize asymmetric T-junctions. Third, Vinotheni established et al. 2020-2025 proposed an adaptive FSM-based system using IR sensors to adjust timings dynamically. It achieved efficiency but required sensor inputs, increasing system complexity. Our project bridges these gaps by creating a compact, hardware-optimized FSM that is specifically designed for T-junctions without needing sensors and achieves high efficiency, reducing waiting time and energy savings. Now, our problem statement. The problem statement for our topic is to design and implement a T-junction traffic light controller using a Moore Finite State Machine in Verilog HDL that efficiently manages traffic flow by minimizing congestion, ensuring safe transitions, and optimizing hardware uses. This controller must be hardware efficient for FPGA development, reliable in all transition states, and scalable for future integration of density sensors or AI-based traffic monitoring. Now, to achieve our goal, we define the following project objectives. Design a 9-state Moore FSM that accurately models the T-junction signal sequence. Second, implement the FSM in Verilog HDL and simulate it using Xilinx Vivado 2025 on an Artix-7 FPGA. Third, achieve over 80% operational efficiency while keeping the design lightweight with less than 20 LUTs. Fourth, ensuring glitch-free and mutually exclusive green signals, which is critical to avoid accidents. Fifth, maintain scalability for future smart traffic upgrades, including sensor-based adaptive control and AI integration. Now, the methodology for this project will be discussed by Swayam Navle.
Our methodology followed a structured hardware design workflow, including system architecture, development, design, defining the input or output, interference, and control flow. Second, FSM modeling, creating a 9-state Moore FSM diagram. Third, HDL implementation, coding the design in Verilog HDL. Fourth, synthesizes and simulation validating the system using Vivado tools. Fifth, analyze and optimization evaluating performance and resource utilization. Inputs. A 100 MHz clock signal which devises all timing operations, an active low reset which initialize the system safely to the default site output. 9 output representing red, yellow, and green lights for the three directions north, south, east, and west. The design ensures stable output, transition, and predictable signal timing, eliminating hazards that occur in merely type designs. Our FSM has 9 states, carefully sequenced and to handle main flow and merge safely. First, main go. North, south, green on for main road traffic. Second, main yield. North, south, yellow on to prepare for stop. Third, all red, all direction red for safety clearance. Fourth, east merge go. East green on for merging traffic. Fifth, east merge yield. East yellow for declaration. Six, all red to buffer before switching direction. 7. West merge go. West green on for traffic flow. 8. West merge yield. West yellow for stop preparation. 9. All red 3. Final all red before cycle reset. A timer counter controls state duration. Each state runs for a fixed number of cycles. Example 20 cycles for main green, 10 for merges, 5 for yellow, and 3 for all red intervals. The 8-bit counter decrements every clock cycle and transitions to next state. This mechanism ensures deterministic and glitch-free control with a complete cycle of 51 clock periods corresponding to 510 nanoseconds at 100 MHz. Here's our block diagram. It consists of FSM controller, holds the state register and next state logic. Timer counter count downs each state duration. Output decoder activities the correct activates the correct control signal combination based on FSM states. This modular structure simplifies design verification and allow easy expansions. For example, additional inputs like density, sensors, and pedestrian button can be added without changing the FSM's core logic. All the modules are designed in Verilog HDL and connected hierarchically. In the top level architecture for synthesize on the Artix-7 FPGA. Here on now, Maitri will talk about results.
After synthesizing and simulating our FSM-based controller, we obtain excellent performance results. Operation efficiency is 80%, average waiting time reduction 25% down to 150 nanoseconds. Logic resource usage only 12 LUTs and 8 flip-flops, representing a 33% reduction compared to traditional design. Power consumption 0.15 millivolt measured in Vivado power analysis. Glitch-free transitions verified in waveform simulation. The simulation waveform showed accurate and smooth state transition. For example, the main green, main yellow, all red, east merge, west merge, and back to main green. No overlapping greens were observed, confirming safe operation. The design also showed a 50% reduction in idling emissions, demonstrating environmental benefits from optimized signal phasing. Now I proceed to conclusion. To conclude, we successfully designed, implemented, and tested a T-junction traffic light controller using Moore Finite State Machine in Verilog HDL. Key outcomes of a project include high, high performance, that is 80% operational efficiency, safety, 100% mutually exclusive light transitions, a low hardware usage, only 12 lookup tables ideal for small FPGAs, reduced waiting time, that is 25%, improvement over static timers, sustainability, 15%, lower idling emissions due to optimized timing. Our design demonstrates how logic and FSMs can effectively contribute to smart city infrastructure. In future scope, we can add integrating infrared sensors for vehicle density detection, adding AI and computer vision models for dynamic signal control, extending to multi-junction network and real-time hardware implementation on FPGA boards. Now, the references we include helped us validate our simulation parameters and align our results with real-time traffic conditions. Now, I thank everyone for their time and attention. We would like to express a heartfelt gratitude to Professor Akhil Masurkar for his constant guidance, encouragement, and technical inputs. We also thank our department and institute for providing the necessary tools and resources for successful completion of our project. Thank you.